Today I'd like to start a short series on the topic of IF transformers. In particular, this is for cases where you're working on a radio and the IF transformer that you have in the radio has been damaged beyond repair. Either somebody's screwdrivered it, broken the cores, or has, as sometimes happens, they'll actually turn the plastic tube or paper tube holding the coils to the point where the wires break off on the terminals. And this happened to me for this particular radio here in the back. This is a Ward's Airline. It's a fairly modern PCB design radio. All the circuits, all the components are mounted on a PC board rather than point-to-point wiring. And it used IF cans very similar to this. And I was repairing the radio and discovered that I couldn't get any sound out of it. Once I took the IF cans apart, I found that one of them had its coil winding form rotated to the point where it had completely destroyed the wire connections. It also had a broken core in it, so there was really no way I could fix it. So what to do? Well, you either scrap the radio or you look for a solution on how you can create your own IF can. And this series of videos is going to document what I came up with. So let's just try the radio out first. I'll just turn it on and we'll go through some stations and see how it works. And then I'll take the back off and we'll take a look at what's inside.
It becomes more of a logistical question, but I like your idea in that if you could make it work in, a perfect world, yeah, give the home.
Abra in Surrey in 2017 and attempted murder.
Staycations are the order of the day, so we thought it a good idea.
The only being a deaf guy who plays.
So the radio reception is not too good down on the main floor here, but on this radio it does pick up most of the AM stations in this area. I've even managed to pull in some stations from as far away as Portland, and I'm actually in the lower mainland in BC, which is on the US-Canadian border on the Canadian side. So that's quite an accomplishment for this little radio. I keep the screws out of this one because it's on and off all the time. It's just easier to work with it when it's just all ready to go. On this particular one, we have to pull the knobs, and then the tubes come out. So as you can see, fairly standard radio layout. We have an American 5 with 2 IF cans. This radio is hiding a little secret. We'll take a further look at it. So I'll just go in here and desolder the cans off of this. Let's see if we can lift up the IF cans without destroying everything. Yep. That's one. And that's two. Now let's get in there for a closer look. So as you can see, obviously these aren't the stock IF cans. These are in fact two prototypes that I made. The first one here uses a different style of choke than this one. These are small, what are called dog bone style axial chokes. And these are radial chokes. And they have slightly different properties. So I've been playing around with them and seeing how they can work. I have found that in general these work better. They have a better, higher Q factor. These have a lower Q factor and you can't really get a good sharp selectivity off of them. This is an initial prototype board, and then I ran off some PC boards and I stuffed one of them, and that's the result of this one here. So what we can do here is we can put another one of these together and perhaps see how that works. So this is one of the panels that I had produced for the version 1 of the IF transformer. And I'm just to get them out easier, I would assume that you could assemble the parts while they're in the panel. I mean, if you're running off a large batch of these, that would make sense. For singletons, I just take the PC board parts out and deal with them on a per board basis. So I'll just go in and I cut one of the tabs on one side. Then it's a simple matter of just breaking it out like that. And we have the parts. Then what I'll do is clean up the part by using a file. Somebody just smooth out the edges and try to get the small connectors islands off. The gap in the top and the bottom parts is the same width as the FR4 material. I have found it to be a little bit on the tight side, so I will just give this a couple of swipes on the tabs of the main body just to clean them up and thin them out a little bit. And it makes the process of putting this together a little bit easier. So what we're left with is 3 components. I'll just take this island out too. So on a traditional IF can, there's a tube, the coil winding, the form, and it has an upper coil and a second lower coil. I believe the lower coil is usually the primary. I would have to check up on that. And then in the body, at the bottom, there's the silver mica capacitors that form the capacitive part of the tank circuit between the two parts of the transformer, which is essentially what this is. An air-coupled primary and secondary tank circuit. The base is designed to fit within IF shield that is 3/4 of an inch by 3/4 of an inch. I haven't yet sourced an IF can, but I have designed this board as well as a 3D printed base for it so that it can actually fit inside of the can once it's finished. The three parts is that this is the main body, which houses the two inductors that replace the coil windings, and then there is room in the bottom and the top for a capacitor to form the bulk of the capacitance for tuning the LC circuit. The top and bottom pieces house the variable capacitor at the top and bottom to trim up the tank circuits. So this part is the top, and this part is the bottom. It's a bit more complicated because there's also some additional pads in there if you want to put in a loading capacitor or loading resistor, I mean, on the output. And this has the effect of decreasing the selectivity and increasing the bandwidth. So the way this fits together is that the bottom part that's indicated primary, secondary here, and there's a primary and secondary on here, fits together like so. And then the top part, I don't think, it doesn't really matter which way it goes. There's really no problem with that. The primary and secondary are noted on the bottom because both the primary and the secondary windings have to exit through the bottom via these 4 leads. But on the top, the only thing on the top is the variable capacitor. And then by actually soldering the pads on either end, we anchor and the top and the bottom together and make it immovable. And then from there, the base is added on, the legs are added, and then the whole thing fits inside of the can. Like so. So as you can see, it's being designed to fit inside of the native can, and you can see there, possibly, the hole in the top can easily reach the variable capacitor, and the hole in the bottom of the 3D printed base allows access to the bottom capacitor. So let's put one of these things together and see how that works. The PC board has been designed to accept either a surface mount capacitor for the bulk of the capacitance on the LC circuit, or a through-hole capacitor can be added here. These are, I think, 805 capacitors, and they can be quite fiddly to put in, and if you're not used to it, it might be easier for you to just order through-hole parts and put them in here. The inductors are designed to go here, and there are markings on the board to indicate the optimal spacing between the two. The spacing is critical. You want about 10 millimeters of space between the two to get the maximum, the best coupling. If they're too close together, it tends to widen the band too much, and you get too many you can get side stations coming in. Ideally, you want a bandwidth in the IF can of 9 kilohertz, but you can narrow that up to reduce interference from side stations if you have a large crowding on the AM dial. I like to sort of keep it around 9 kilohertz. I think that's a fairly comfortable bandwidth for these. So I'm going to use through-hole parts for this, and I'm going to start by putting the inductors in. I like to put the inductors in, both of them facing the same direction, just to make sure that the windings are the same. It probably doesn't matter, but it just makes my life easier. If there's any problems, I know that's not one of them. So I like to bend the wire leads on these, and then what I will do is I'll form the leads around a tool, screwdriver, or something else, so that you want to get something like that. And this makes it easier to space the inductors apart. And then inductor simply fits into the hole like that and drops in, and then we can put the other one in. See, we want to go around like so. I will then just solder them on there. And we've gone through the... No, we'll just solder them on the other side just to make sure. I think on the next version of the board I'll make the lead holes a bit bigger. Make it a bit easier for the solder to wick through. Next we can add the capacitors. I'm not going to trim the capacitor leads right now. I may swap them out for a different value if I am not within the center frequency that I like. Of course, for this IF can, we're looking at 455 kilohertz for the center frequency, or the IF frequency. The circuit is fairly flexible. I mean, if you have an IF can that has to be 450 kilohertz or even as far down as 300 kilohertz, you could create a capacitor inductor combination that could make that fairly easily. Although you may have to change the gap between the inductors to improve the Q factor, the coupling factor. So that's basically it for the main board. On this IF can, I'm not going to put a loading resistor on the secondary. We'll just leave that off for now. We'll just put the trim capacitors on. And these are surface mount trim capacitors. So advantages, well, they're small. Disadvantages, well, they're small. They can be tricky to tune, especially trying to find the little screw here in the center by fishing through the top of the IF can be frustrating sometimes. I can look into using through-hole variable capacitors at some point, but the problem with those is that they're very hard to find, whereas surface mount trim caps are readily available from places like Digikey, Mauser. So when putting these on, I like to just wet one side and bring it up. Take a look at it. Yeah, seems to be okay. I think we're good there. Now the next part is to assemble the unit together and with the top and bottom PC boards. So the way this goes together, again, there is a top and a bottom. The indentations on the vertical board here denote that goes down this way. This is the bottom piece, and the indentations are there so that it can fit inside of the base. And of course there's a primary and a secondary on this. There's the primary there, and primary there. The secondary is on the other side of the board. You want to try and get the boards to line up. That's why filing the tabs helps, because then you can slide it back and forth. But you want to get that lined up on the edges so that it can go inside of the base very easily. So that looks good. We'll just solder that. Don't solder both sides at the same time, just alternate back and forth. The lead will shrink a little bit as it's cooling, or the solder will shrink a little bit as it's cooling, and so you'll get a distortion if you solder both sides at the same time. And what I like to do is, like, once it's actually set, I'll go back and I'll reheat the joints just to make sure that it's not pulling to one side or another. we go. Again, try to center up the top board so it's flush on both sides. It's not an ideal mechanical bond, but really there's not a lot of stresses or forces on the IF transformer assembly once it's in the can. The tuning tool comes right down the center, so there's really no strain on this. So it should be fine. I don't think it needs any additional stress or mechanical attachments. And you could add some wire in there, drill some holes, but I doubt that it really needs that. Long-term testing will determine whether it can handle the heating and cooling cycles in the radio and prevent the solder joints from stressing, crystallizing, and becoming cold solder joints. So that's the entire can assembled. The next step would be to try some preliminary tuning on it and see if we can get this thing to couple together at 455 nicely. So I moved to the second bench here where all my equipment is, just for convenience. The light is not so good here, so it will be a little bit perhaps dark, but I pulled down 2 instruments here so we can play around with the transformer. I've soldered on some legs just to make it easier to hook on the test equipment, but other than that I haven't really touched the transformer. So what we want to do, and this is the way I like to test them. There are several ways to do it, but I've found that this one works pretty good and gives me good results. So here's our signal generator, and it has a 50 ohm load, and 50 ohms is a bit too low to load down the transformer winding. So what I do is I'll bring the impedance up a little bit by adding in a 4.7K resistor here. I'll couple that into one of the windings, and then this will be the ground, and this is our first tank circuit, the primary, and then the secondary is on this side. There's also a bulk capacitor in here. I'm just not putting it in the diagram. This goes off to the scope. And the scope is grounded on this side, and the scope probe is put on the other side of the secondary. The waveform generator is set to 455 kilohertz, which is our ideal frequency. I've got the scope running at 1 volt per division for convenience. I think our amplitude here is 1 volt RMS, so it should be fairly comparable. Then we'll just hook up the circuit. We want to have the primary. The primary is the lower one, and the secondary is the upper one. So we want to, first of all, tune the secondary circuit, which is the upper one, by injecting the signal into the primary. So there's our signal source. It's now feeding into the primary. I'll hook the scope up to the secondary. And as you can see, we're seeing a signal there. It's not very tall, maybe 1 volt peak to peak. When the shield is added on to the circuit, this amplitude on the secondary diminishes quite a lot. But with an unshielded can here, unloaded on the secondary, you will see quite a lot of gain in the secondary circuit. So just take the tuning tool. Also keep in mind that grabbing it, you have to be careful where you touch this because it can affect the coupling of the transformer. So now I'm just going to tune it to get a peak as best as I can. This is just a rough tuning. We can move it back and forth over the range, see how close we are. We're out by a kilohertz. So, but that's good enough. We'll have to retune it once it's in the radio circuit. So what we'll do now is we'll switch sides and we'll tune the primary side. And of course the primary side is on the other side of the board, so it's actually in here. So now we have tweaked it. I can tweak it a little bit more perhaps. But we're pretty good. So you can see as we go up and down, we have a maximum there at 455. So it should be good to go. Just as a side note, you can take a look at the properties of what happens when the coils are moved closer together or further apart. This tends to change the properties in that the coupling factor, of course, will change. The gain will change. The Q factor will change, which is the selectivity. So we can now assemble the new IF transformer. I cleaned up the plastic. This is just PLA, 3D printed. It has a low melting temperature, but I haven't really seen an issue with it. Perhaps it'll melt over long durations. I think using a higher temperature plastic in the long run would be better. This is a prototype run that I did. So just fit that in there, push it in, down, get them in there. Make note of which side's the primary. So we have the primary there. Also, another thing I want to show is that the previous shot of me tweaking on these chokes to position them was not in shot, so I'll just add this in again to show how I do it. So using the lines on the board, I want to make sure that I've pushed this so it's aligned with those, and similarly this one here, get it aligned and get them parallel with one another, and that's roughly where I keep it. Now the primary is on the top side, so I've got this one here marked in and out, so I can just use this as a guide, so I know that in is the primary, and then it just fits in the chassis like that. And we can adjust the primary with the bottom hole, and we can adjust the secondary with access to the top capacitor. So that's ready to go in. Next is to put it inside the radio. We'll take the prototype one out and put this one in. Primary. Go. Okay. Sloppy lead dressing on the first one I put in. That's more or less it. As you can see, I've got both of them in there. I have to put shield cans on them now. Ideally, you would put the shield on and then put the whole assembly into the board, just to make life a little bit easier. Just as a demonstration though, to show that I'm actually putting an actual reproduction can in. I'm just doing it the hard way. tube's in the way. I think it's not getting into the hole there. Needs a little persuasion. There we go. So we're good on the first IF. We can solder the shield back on that one. Second shield is not as well done, but I think it'll work. Just have to get it grounded. I'm gonna probably take it back out again. This is my prototype test radio, so I'm constantly soldering and desoldering stuff on and off of this thing. But there we go. Essentially, we got the this prototype out, and we have a new prototype in. So let's see how it works. So let's take the opportunity now to power this up. To tell you the truth, this is the second take, and I'll show you in a minute why. The first time I powered this up, I heard something really nasty, and we'll take a look at that. I've got the AC plugged in to an isolation transformer, and I've got it on a dim bulb on my second bench, so less chance of blasting myself. One of the disadvantages of these PC boards is it's pretty hard to move it around without touching a trace, and if that trace is hot, you're going to get zapped. So you have to be very cautious about what you're doing when you have the board out and you're trying to align it. So I'll just turn the unit on now. And oh no, there's a problem. What happened? It's just horrible. You got this buzzing, clicking noise. No matter what, I can't tune it. It doesn't go away. What did I do wrong? Well, I didn't do anything wrong. You see this? This is my second soldering station, and there's a little MOSFET in there that's switching on and off and on and off and on and off to heat up the tip. Turn off the soldering iron. Dope! So, back to the tuning. So let's bring this up a little bit.
People support online via call centers.
Find the station.
To get troubleshooting help.
And see if we can actually make this sound a little bit better.
Those are the examples of the support that we've offered for Windows 7, and Microsoft will
Now,
no longer
I'm doing this by hearing. This is not the best way to do it. You should be using a scope tied into the AVC, or use a wobulator or some other method to sweep across and tune the IFs a bit better. But just as a first stab at this, I can come in and
share their stories of hope and inspiration in a salute to
find the
join us for this
tuning cap and
bringing the country closer and making a difference. Stronger
find a
together,
peak.
Canadians in support
Go back and do this
of
one.
COVID-19 relief. Sunday at 6:30 on CTV, CBC, Global, and CBTV. During these unprecedented times,
Try and carefully lift up the board. See if we can get a better coverage of the station. Again, being very careful.
Redefine our history. Introducing Pocket Pills, the new online pharmacy that delivers.
That's good enough. This, while I was going through and trying to troubleshoot the horrendous noise, I took the opportunity of putting a loading resistor on the secondary of the second IF. This is going into the detector, the 12AV6. And this is a 1 meg resistor. It helps to load down the secondary a bit and give a bit more, spread the band a little bit in terms of the bandwidth of the second IF.
Will use as they reopen businesses, schools, and other institutions. He says the
So that's
focus
pretty good.
will remain
We'll
on
button it up
preventing the
and
spread
play
of the
around with it a
virus
little bit.
through physical.
So the radio's all buttoned up and we can now play around with it. I don't have any screws in the back or anything. I just push it all back together because I take this thing apart regularly to play around with IF prototypes and other things. This is not really a shelf queen. This is just more of a test bed that I'm using for testing out various things. This is the second IF can we took out and we replaced it with one that we assembled from the board. As I said, I don't really like these chokes. They tend to be a little bit more heavy duty. They're designed for power supplies or for higher current, and I think the interwinding capacitance is a bit much on these. They don't tend to have a very high Q factor, so selectivity is not so good with these ones.
How successful a venture was that for UFC?
The fish and seafood industry. From the Global News Desk, I'm Erin Ubell.
The best way to get the energy generation moving. One of the books, and you and I cover our seminars, and the latest December 2019, January.
Approaching the evening.
England cave warriors, not
Sunday night with an around the 8.
This is not a terribly good radio. There's a lot of noise on it, but it is picking up stations. It seems to be fairly selective. There's not a lot of AM stations in Lower Mainland right now, and this location in where I'm at right now doesn't have good reception. So anyway, that about wraps it up. In the next part, I'll go through the theory of the transformer, go through some of the history of how I came up with the design. I'd like to emphasize that this is not my original idea. This is actually something I found on the forums, and we'll go through that as well, see where I found the source of the information. We'll take a look at the jig I created to test the idea out and to test different components, and I'll try to get that together within the week or so and post another video on this topic. Regarding the boards, I do have boards here. I could potentially put them up on Tindy or something if there's enough interest. It's fairly rare that you have to actually completely replace an IF can, and you'd only need to do this if you didn't have any old stock. Having said that, it's an interesting experience, and it's kind of fascinating that something like this technology can be used in an old radio, and it does work. Is it the best solution? The windings are going to have a high intercapacitance, but as noted in the original forums, it's trying to get it perfect is a bit like trying to put lipstick on a pig. I mean, it's just a 5-tube radio, and you just need to get it good enough so that the IF can get through the cans, get through the stages, and get amplified. And you have enough selectivity to make sure that you're not picking up 2 stations at once. So anyway, that's about it, and I'll wrap this one up. I hope everybody's doing okay in these times, and wishing everybody the best and to take care. I'll talk to you later. Bye.